In this example, we would like to evaluate this double integral of e to the x squared plus y squared dy dx, where R is the semicircular regions bounded by the x-axis and the curve
y equal to square root of 1 minus x squared.
So this is the regions of considerations. So if you proceed with these calculations using rectangular coordinate system, it's doable, but it gets quite complicated very quickly. So we want to avoid doing that. Instead, we're going to convert this double integral into a polar coordinate system. So the first thing that we need to do is we need to convert the surface from rectangular coordinate system to polar coordinate system. So for e to the x squared plus y squared, we can rewrite that as e to the r squared. And for the regions of integrations, instead of r equal to the set of on the point x, y, where y is bounded between 0 and square root of 1 minus x squared, and x is bounded between -1 and 1, we're going to rewrite these regions in terms of polar coordinate system as follows. So r of theta. To get r, we're going to draw a ray going from the smallest point to the highest point. That is r is between 0 and 1. And we're going to draw an arc going from the smaller angle to the bigger angle, and theta is between 0 and pi. Now the volume is calculated using the double integral of r dr d theta, and the function of consideration in this case is e to the r squared. So you have e to the r squared, and I'm going to move this closer, for r running from 0 to 1 and theta going from 0 to pi. To evaluate the inner integral with respect to r, I'm going to use integration by substitutions by letting u equal to r squared. Therefore, du is equal to 2r dr. We're going to solve for dr, and we get 1 over 2r du. Because you make the change in the variable, we're going to change in the limit of integration for the inner integral as well. So this table consists of 2 columns. One column is for r, the other column is for u is equal to r squared. When r is equal to 0, u equal to 0. When r is equal to 1, u is equal to 1. So the double integral becomes the integral from 0 to pi, and the integral from 0 to 1 again, of e to the u times r. Now dr is equal to 1 over 2r du, and then d theta. And r cancel out, and you get 1/2 e to the u du, but 1/2 is a constant multiple, so you can pull that out of the integral operations. You get the integral from 0 to pi of 1/2 times the integral from 0 to 1 of e to the u du, d theta. The integral from 0 to pi of 1/2 e to the u, evaluate at 0, 1 d theta. And you get the integral from 0 to pi of 1/2 e to the 1 minus e to the 0 d theta, or the integral from 0 to pi of 1/2 times e minus 1 d theta. And this expression is just a constant, right? You can pull that out of the integral operations and take the integral with respect to theta. We're going to get 1/2 e minus 1 theta, evaluate at 0 and pi. Or we're going to get the answer of 1/2 times e minus 1 times pi. And that is the answer. In the next example, we would like to compute the double integral of x plus y over a domain D, where D is the quarter annulus. Again, the idea for this lecture is to convert everything from rectangular coordinate system to polar coordinate system. And here, the first thing I need to convert is the surface x plus y. So x plus y, written in polar coordinate system as follows. This is equal to r times cosine of theta plus r times sine of theta. And we're going to take r as a common factor, and we're left with cosine of theta plus sine of theta. So the domain D, instead of on the point x, y, for x is between 2 and 4, and y is between g1 of x, g2 of x. We're going to convert this into the domain in terms of the polar coordinate system, which, as you can see, is a lot easier to obtain. So this regions or the domain point is the set of on the point r, theta, such that r is between. Now, to find the value of r, you're going to draw a ray going from the smaller r to the bigger r, and you see that r is bounded between 2 and 4, whereas theta is bounded between theta equal to 0 to theta equal to pi over 2. Now the double integral for the volume of x plus y dA over the regions D can be written in terms of polar coordinate system as r times cosine of theta plus sine of theta times r dr d theta for r is running from 2 to 4 and theta is between 0 and pi over 2. Now we're going to manipulate the integrand, and you got the double integral from 0 to pi over 2 and from 2 to 4 of r squared times cosine of theta plus sine of theta dr d theta. Now for the inner integral, the integral is with respect to r, so therefore cosine of theta plus sine of theta is a constant. So the antiderivative of r squared with respect to r is 1/3 r cubed times cosine of theta plus sine of theta, evaluate at 2 and 4, d theta. And we're going to evaluate the function at 2 and 4, you get 1/3 times cosine of theta plus sine of theta times 4 cubed minus 2 cubed d theta. And if we do this calculations correctly, you're going to get 56. So you get, and 56 over 3 is a constant in this context, so you pull that out of the integral operations, and you get 56 over 3 times the integral from 0 to pi over 2 of cosine of theta plus sine of theta d theta. And you're going to take antiderivative of cosine of theta and sine of theta with respect to theta. You're going to get sine of theta minus cosine of theta, evaluate at 0 and pi over 2. So here is the evaluations. So sine of theta at pi over 2 and 0, so you get sine of pi over 2 minus sine of 0, minus cosine of theta, that is cosine of pi over 2 minus cosine of 0. Sine of pi over 2 is equal to 1. Sine of 0 is equal to 0. Cosine of pi over 2 is equal to 0. And cosine of 0 is equal to 1. So we get the evaluation of 56 over 3 times 1 minus negative 1. Or 2 for the answer in the parentheses. Multiplied with 56 over 3, we're going to get 112 over 3. And that's it for this evaluation. So let's move on to another topic. In the last lecture, we generalized double integrals over rectangular regions to double integrals over non-rectangular regions. In a similar manner, the method for integrating over a polar rectangle may be extended to more general regions. Now consider a region described in polar coordinates bounded by two rays of theta equal to alpha and theta equal to beta, and two curves where r is equal to g of theta and r is equal to h of theta. And we can put this into a theorem where you can calculate the double integral of a surface over a regions on the xy plane in polar coordinate system as follow. So let f be a continuous on the region r in the xy plane expressed in the polar coordinate as r equal to the set up on the point r comma theta such that r is bounded between g of theta and h of theta, and theta is bounded between alpha and beta. Then you have that the double integral of the form f of xy dA over the region r can be written as the double integral of f of r cosine of theta, comma r times sine of theta, times r dr d theta for r bounded between g of theta and h of theta, and theta is bounded between alpha and beta. Now the regions of integrations can be visualized as follow here. So you have the regions in brown. The region is bounded by two rays, theta equal to alpha and theta equal to beta, and also bounded by the two curves r equal to g of theta and r is equal to h of theta. And this is the formula to evaluate the volume of the solid bounded by the surface z of f of xy and the regions on the xy plane, but they're written in terms of the polar coordinate system. So let's consider the following example. We would like to use a double integral to find the area enclosed by one loop of the four leaf rows with the formula in the form of r equal to cosine of 2 theta. And as you can see in the figure here, theta is bounded between negative pi over 4 and pi over 4, whereas r is bounded between 0 and the curve cosine of 2 theta. Therefore, you can set up the formula as follow. Remember, in this calculation is the area, so you don't need the function value in the double integral. This is equal to the double integral of 1 times r dr d theta for r is between 0 and cosine of 2 theta, and theta is between negative pi over 4 to pi over 4. Now we're going to evaluate this double integral. So the inner integral is evaluated as follow. So the outer integral is from negative pi over 4 to pi over 4. The antiderivative of r with respect to r give you 1/2 r squared, evaluate at 0 cosine of 2 theta d theta. And you evaluate the functions as cosine of 2 theta and 0. You get the integral from negative pi over 4 to pi over 4 of 1/2 times cosine squared of 2 theta d theta. Now you have the integral in terms of theta, and this is not a straightforward integral to evaluate. What you do is you have to convert cosine squared of 2 theta into cosine of 4 theta using the double angle formula. So we get the following integral. The integral from negative pi over 4 to pi over 4 of 1/2 times 1/2 times 1 plus cosine of 4 theta. What I did is that I rewrite cosine squared of 2 theta into 1 plus cosine of 4 theta altogether divided by 2, or you take out the 1/2 here. So this formula is called the double angle formula. This is one of the trigonometric identity. Okay, so here I have 1/2 times 1/2 becomes 1/4, and I can bring that out of the integral operations. And again, 1/4 times the integral from negative pi over 4 to pi over 4. I left with the integrand of 1 plus cosine of 4 theta d theta. So antiderivative of 1 with respect to theta is just theta. Antiderivative of cosine of 4 theta with respect to theta, you're going to get the antiderivative of the form plus 1 over 4 times sine of 4 theta, and this evaluate at negative pi over 4 to pi over 4. So at this point, you can evaluate the function at these two limit of integrations, and we're going to get 1 over 4. Now you have pi over 4 minus negative pi over 4. Plus 1/4 times sine of 4 times pi over 4 minus sine of 4 times negative pi over 4, which is going to be negative pi. So sine of 4 times pi over 4 is also going to be equal to pi. Therefore, sine of pi is equal to 0. And sine of negative pi is also equal to 0. And we're left with the calculations of 1/4 times pi over 4 plus pi over 4. Or you get pi over 2, or altogether we're going to get pi over 8 for the answer. So pi over 8 in this particular example is the area of the one loop of the 4 leaf rows of the form r equal to cosine of 2 theta. So this is not the regular volume calculation as you see in so many examples already up to this point. And because of the calculations of the area only, we did not include the function value in the double integral. So I hope you see the difference between what we have done so far with what this example presents. Now let's move on to the last example. So in this example, what we want to do is just write an iterative integral in polar coordinate of this function, g of r theta dA over the regions r, where r is the regions outside the circle r equal to 2. So this is the circle of r equal to 2. And inside the circle of r equal to 4 cosine of theta. So the regions of consideration is in brown here. So the circle r equal to 2 is the circle with radius 2 center at the origin. And the circle r equal to 4 times cosine of theta is the circle with radius 2 center at the point 2, 0. So here's the setup. And remember, we just want to set up the integral, and the integral has to be written in the polar coordinate system. So the double integral of interest is of this form. The double integral of g of r theta dA over the regions r. Because there's no specific function of consideration, we're just going to write g of r theta. And dA, the area, when it's written in terms of the polar coordinate system, it consists of r, dr, d theta. And what about the bound of r and of theta? So for the bound of r, as you can see, this is the regions of considerations. If you put a rate in the regions, you can see that one side touches the curve, the left side touches the red curve, that is r equal to 2, and the right side touches the black curve, which is r equal to 4 times cosine of theta. So therefore, the lower limit of integrations of r is 2, and the upper limit of integrations of r is 4 times cosine of theta. To get the bound of theta, you're going to look at the intersection point between the two curves. As presented here in the figure, you see that theta is between negative pi over 3 to pi over 3. So you can write negative pi over 3 to pi over 3. But how can we obtain this number if they are not described in the figure? So it's actually not as difficult as you may think. It's just that you just need to find the intersection point between the two curves, the red curve and the black curve. So you have the red curve is of the form r equal to 2, and the black curve is the equations of the form r equal to 4 times cosine of theta. And you're going to set these two equations equal to one another, and you get the equations of the form 4 times cosine of theta equal to 2, or cosine of theta equal to 1/2. When cosine of theta equal to 1/2, there one possibility for the solutions of theta is that theta equal to pi over 3. Another option, if you rotate theta in the counterclockwise directions, another solutions that you can have is 5 pi over 3. That is, if you want to rotate the angle in this particular directions. However, that is not what we are looking for. What we are looking for is the angle that go in the clockwise directions that way. So therefore, instead of theta equal to 5 pi over 3, you have theta equal to negative pi over 3, because again, you want to rotate in the clockwise directions, and because the curve or the regions of considerations is presented in this particular manner. So another solutions that we can get is theta equal to negative pi over 3. So that's why for the limit of integrations of theta, you get theta is bounded between negative pi over 3 and pi over 3. So that's it for me. So in this lecture, we look at the double integral in polar coordinate. And not only we write the double integral in terms of polar coordinate system, but for the regions of integrations, we look at polar rectangles and a more general polar regions. So that's it for me. Please let me know if you have any questions. Thank you.